Hello everyone, I'm Seung Kim from University of Seoul. In this talk, I'm going to present our work of minimizing GPU kernel launch overhead in CNN Inference, the recent mobile GPU. This work is done with my advisor, Professor Youngmin Lee. I'll first introduce the trend and background. After the problem statement, I'll explain the two proposed approaches to tackle this problem. Then I'll show the evaluation result, followed by conclusion and future work. The performance of mobile GPUs has been constantly increasing. During the last decade, the throughput of a mobile GPU has increased by 346 times. NPU have high energy efficiency, but they own disadvantages. And we envision that the mobile GPUs will continue to be used as the dual accelerators. Another trend is that the CNN model is getting lightweight for the mobile platforms. The number of operation in mobile FE1 is only 5% of inception V4, and it takes only 6.5 milliseconds on Adreno 630 in Snapdragon 845. As the CNN models are becoming lighter and the mobile GPU becomes faster, the kernel launch overhead becomes a performance bottleneck. Since CNN layers are executed one layer by one layer, and a layer is implemented as even several OpenCL kernel, it results in many kernel launches. Effective kernel launch overhead or shortly CLO, which we defined as the end-to-end latency minus sum of execution time all of kernels, accounts for 15 to 13% in many recent CNN, and it takes even over 60% or some cases. To understand the CLO, this slide illustrates how the kernels are launched and issued via the command queue between OpenCL host and the device. After the OpenCL host set up the command queue in initial step, it enqueues the kernels to the command queue and flush the queue using shell flush API to issue commands to the device. Simply put, effective CLO is mainly caused by the GPU idle time between kernel executions. When the GPU kernel executions are too fast compared to host preparation for next kernel and launch overhead, then GPU becomes idle. One can think of reducing the GPU idle time by flushing the command queue at every kernel launch. However, this is not optimal because shell flush API itself takes some time. Let me explain this with some example. When a kernel I is launched at T0, there is some in-queue overhead there we denote by base CLO or big CLO. Then the host advanced to T2, preparing the next kernel launch. After launching kernel I+1 at T2, the host calls shell flush at T3. The yellow is the shell flush overhead in host, and the light blue is the related overhead in the GPU. Then the two kernel launch commands in the queue are flushed. Each kernel starts to run sequentially, preceded by some overhead which we denote by GPU equal to. Note that as can be seen here, some part of host time and base clock is hidden are hidden by the GPU kernel execution time. So the effective clock or clock in this example can be highlighted like this. And we can see the clock can be minimized if the host overhead and processing time can be hidden by GPU execution time. Thus, the research problem of this work can be started as minimizing CNN inference latency uh, by hiding host's processing time and base clock in the GPU executions, which can be achieved by flushing the command queue at proper time. In other words, it is about how one can find the optimal timing for the shell flush to CNN inference latency. One simple approach is to apply some constant period of k in terms of the number of OpenCL kernels to call shell flush. For example, in TensorFlow Lite, the period k of shell flush is 24 for Mali GPU and 1 for PowerVR GPU. In ARM computer library, shell flush is called after the last GPU kernel of each convolution layer. However, we found that these are not optimal. This slide shows the proposed approach to tackle the problem. We first developed the clone model that captures the underlying factors and hence can predict the optimal period k of shell flush. And we can also use lookup table based approach, which is more error robust and sometimes more practical. This figure shows the overview of a proposed approach. First, the clone model or lookup table is constructed for the target device. Then the host processing time and GPU kernel execution time are profiled. Next, static and dynamic shell flush scheduler find out the optimal period k using k clone model or LUT with profiled time. Finally, shell flush is executed in the DL framework according to the optimal period k. We have modified at DL framework a little bit to incorporate these components. The clone model we developed takes some factors as input variables and the other as some constant. The input variables are processing time, tprod, kernel execution time, or tcur, and shell flush overhead. tprod and tcur are determined by CNN models, the DL framework, and the GPU used, while shell flush overhead and other base clock are determined by the GPU and CPU. And to make problem simple, we assume that tprod and tcur should be the same across the layers. What we observed in modeling of clock is that clock is linearly proportional to tprod. The graph below shows the clock value when tprod and tcur change, while the shell flush period k varies. With a fixed tcur, clock is represented as two lines that intersect at a threshold point, and we only need to figure out the linear equation for these regions. Threshold curve is a set of threshold points that divided the two lines, and it corresponds to the case in which host time and GPU time becomes equal. As shown in the figure and equation, thost included k times of pprod and CPU Piccolo plus one CL flush overhead. Uh, tGPU, in the other hand, include one GPU Piccolo 1 plus k times of Piccolo 2 and kernel executions. When thost is less than tGPU, we call it this region threshold sub-threshold region. It is in turn divided into two phases. In initial phase, the host includes k kernels and calls the shell flush. In ongoing phase, uh, as thost is less than tGPU, other overheads except GPU Piccolo 2 are all hidden by GPU execution time. Thus, it can be represented as linearly proportional to deep food. On the contrary, when thost is larger than tGPU, we call it super threshold region. The clue in this region is same as the clue in sub-threshold region plus some extra time, which we denote here by alpha. When t-threshold is defined as default when t-host equal to tGPU, here the upper figure alpha is equal to default minus t-threshold. Here the upper figure is when thost equals to tGPU, while the low figure is for super threshold region. After redistributing the time in the upper figure, it is clear that the extra time in lower figure is alpha times k for each flush. And during entire inference, the CPU suffers from alpha times the number of kernels in total. Thus, this equation is represented as linearly proportional to default. In summary, the model can predict clock using a tuple of k default ticker. It consists of two lines given k and ticker and slopes and intercept can be calculated by measuring flow with a set of tuples. And the shell flush overhead and base color is target specific and are captured in the model. As a result, we can predict the optimal period k that minimize color for any producing time and kernel execution time. Ideally, only 3 measurements should be sufficient to identify the two lines. In reality, measurement errors exist because the values are quite small. They are typically in microsecond orders, and the model can be inaccurately constructed. Thus, we propose lookup table-based approach where the default and ticker becomes the rows and columns. The optimal k for this pair are individually measured and filled in. Thus, even if there is a measurement error, it can be affect the optimal k value in other cells. We propose three schemes that we can be largely divided into static and dynamic ones, which we will explain this one by one. The first scheme is constant k scheme. It used the average default and ticker of the kernel in the CNN model. Once the k value is obtained from the table, it is used throughout the CNN inference. The second scheme is static variable k. In this scheme, we use individual default and ticker instead of average value of all kernels. This scheme can be effective when the default and decal of each kernel can vary a lot. It is still a static approach in that default and decal are profiled on offline, and the location to call shell flush is determined in advance. But value k is not constant and can be variable. The input of this algorithm are the profiled default and decal, and the output of the output of is flush, and the binary flags for flushing the kernel. The flags are initially set to first while it iterates over the kernel. If is flush is true, it calls the shell flush and found out the next location to flush using lookup table. Dynamic variable k is similar to a static variable k scheme in that k value changes employing the same algorithm. But default is not profiled offline, but it measured at runtime. It makes it adaptive to the change in the host, such as UI interrupt and other process, and the preemption of the other process, and so forth. The overhead of measuring T-food is less than 0.1% of the total time. For ticker, we still use statically profiled value because they have a very small deviation. We can avoid costly profiling with OpenCL event at runtime. Now let me show the experimental results we use two devices. For the deep learning frameworks, we use ARM computer library and TensorFlow Lite. The default type is FP32 in ACL, while it is FP16 in TF-Lite. Note that we use task set so that the host process is not scheduled on little core to reduce deviation on measurement. First, we manually found the optimal k in brute force way in order to see the ideal speed of the constant k scheme. As the table, the speedup is up to 1.3 times for Exynos on HL with mobile FE1. This slide shows the speedup of three lookup table-based approach. The baseline is default scheme in each deep learning framework. In Asia, the default scheme is to shell flush after the last kernel of shell combo layer, and in TF-Lite, it is called shell flush at every 24 kernels for Mali and no flush for Adreno. As can be seen in the figure, the proposed constant scheme is better than the default scheme in deep learning frameworks. It is up to 1.64 times of the speed up on overlap V1 0.25. Static variable k scheme has possibly to achieve a larger speed up than constant k scheme, and but it is no larger than as we expected, and quite similar in many cases. Dynamic variable k in this graph is not particularly better than the other schemes because there are no much dynamics in the experiment conditions. In this slide, the speed up of Clo model is shown and compared with that of the LUT-based one. Uh, the speed up of Clo model is smaller than that of the LUT-based one due to the inaccurate slope value in a Clo model caused by measurement errors. Lastly, this slide shows the power consumption and the energy efficiency of constant K scheme on Snapdragon. We used the Snapdragon profiler to measure the power consumption of the chip. As shown in the green bar, the proposed scheme is more, more or less similar to the default scheme, while energy efficiency energy efficiency is usually higher as shown in the black line graph. It is up to 29% more efficient than the ACL default scheme because of the reduced inference latency. In summary, we observed that Clo is large in the lightweight channel, including mobile LED on recent mobile GPU. Clo can be minimized by share plus timing optimization, and we proposed Clo-based approach and LUT-based approach. We formulated a complex kernel launch process into simple linear models called the Clo model, and we proposed LUT-based optimization to effectively estimate share plus period K. As a result, we could achieve large speed up with simple software adjustment in the widely used deep learning frameworks. There still remain many research challenges we did not consider in this work. First, we tried to minimizing the latency without any design constraint. However, one can solve other optimization problem with some constraint using Clo model. It could be a power minimization with latency or a throughput constraint in real-time systems, for example. And we focused on single DNA inference in this work, but one can formulate the Clo model or design the scheduler that can consider a concurrent execution of multiple DNA on the same device. With that, I would be happy to take any questions. Thank you.